Now we can start the second session of our today workshop. It's a pleasure for me to introduce Bartek Gardas. The pleasure is because in some sense he is my product, because I used to be his supervisor of his PhD thesis. Of course, it was not a very hard job to be his supervisor, because he's quite a clever guy. Yeah. But nevertheless, my CV is much richer because of him. Okay?
Yeah, thank you, Jurek, for this very nice introduction. I'm starting the second panel, which means the remaining talks will be more technical than the previous ones. But don't be worried, stay tuned, and hopefully you'll learn something interesting. And today I'm going to be talking about defects in quantum computers, especially about defects in D-Wave. So let me start by saying that I think that already Bo and Danny made that perfectly clear, that to perform quantum computing, one needs adiabatic evolution. So what does it mean? So usually we say that a quantum system evolves adiabatically when it evolves very slowly. That's probably true, but it's still a very rough definition. So I don't want to go into unnecessary details what the quantum adiabatic evolution is. Personally, I like to think of adiabaticity as, I like to compare adiabaticity to the aging process. It's like every day we look at the mirror and it's really hard to spot any changes that might have happened during the night, assuming of course you're not strongly hungover. But when you grab pictures from 3 years back, it will be almost immediately obvious that so many things have changed. And this is basically what the adiabatic evolution is all about. Locally, everything looks static, as if nothing really changes, but globally, over a long period of time, you can see that a lot of things have changed. So at this point, we could ask, is it always possible to make a quantum system to evolve adiabatically? And of course, I can imagine a situation where even a small change is done to a quantum system will be so severe that I will lose entirely the control over its evolution. That can happen, of course. So I don't want to talk about that kind of systems here, but there's yet another scenario that can occur. And so imagine that your evolution is adiabatic, but not entirely. So there's going to be a period of time during which the system cannot, for some reasons, evolve in an adiabatic way. So first question that we should be asking ourselves at this point is, can we actually realize such systems in D-Wave? And the short answer is yes, we can. And here you can see primary examples of that on the left. This is actually a chain of qubits. This is a one simple string of qubits. So I'm taking the one qubit and connecting that to the second one to its nearest neighbors. And you can see that even probably in a more clear way on the right. So this system is called by us physicists a quantum Ising model. This one in particular is called a transverse Ising model. And speaking of being mathematic about it, the Hamiltonian looks like this. It's, of course, the system is time dependent. You have two functions called delta and epsilon that depend on time, of course. And as you can see what happens here, and this is exactly what happens in general in D-Wave. I'm going to describe that shortly for this particular model, but what I'm going to say next will be true for all couplings that you can imagine realizing in D-Wave. So at the beginning, as you can see, this guy over here dominates. So the interaction between qubits is basically negligible, and the magnetic field is huge. And as a result of this, all spins will be pointing in the one, in this case, x direction. And this is a very nice situation because, well, this is the quantum state that I can actually prepare in D-Wave. It's extremely easy to arrange spins to point like this. But on the other hand, this state is completely useless for calculations because I have no interaction between qubits because this guy over here is basically 0. So to make some processing, to process information, I need non-zero couplings. And this is exactly what happens in D-Wave next. As you can see, I'm lowering this magnetic field, and at the same time, I'm increasing the interaction between qubits. So you could say that in principle your capability of performing computation increases as you increase this coupling between qubits, right? And presumably in D-Wave what happens is that this evolution is adiabatic. So this S parameter here is just time divided by something which is called the annealing time, and you can think of it as being one D-Wave processor cycle. So we all understand for classical computing that processors operate over cycles. So for D-Wave, time necessary to complete one cycle is called the annealing time. And we, of course, assume that during this evolution, the system will remain in the adiabatic evolution. So assume now for a moment that I cannot actually satisfy this condition. And as a result of that, there's going to be a lack of adiabaticity, and I will create, as a result, I will create something which is called defects, right? So there's a theory behind those defects. It's called Keeble-Jurek mechanism. After Keeble, that passed away a couple of weeks ago, actually. It's a real loss. And Wojciech Jurek, that is currently my mentor in Los Alamos. And basically, this theory predicts that the number of topological defects should scale as a function of the speed. And now, we can actually understand what really happens here. So the system I've been talking about is a system that undergoes a quantum phase transition. So there is a specific value of a parameter that I'm changing, and when I'm crossing this specific value, the system is changing phases. So it's like the system is changing its very nature. I basically dealing with a different system after crossing the critical point. And what is really exciting about that is the number of topological defects that I will create at the end of my evolution only depends on the speed at which I'm crossing this critical point. And let me emphasize something before I proceed any further. By defects, I don't necessarily mean something which is bad for quantum computers. It's only a name. Actually, I should refer to them as topological defects, but the name would maybe probably be more confusing than it already is, so I just leave it as defects. But keep in mind that defects do not mean something which is bad. And of course, I know the scheduling, D-Wave scheduling, so I know how those delta and epsilon functions change over time, so I can deduce what the speed is. And the speed, of course, will depend on both couplings between qubits and the annealing time, which again is the time necessary to perform one cycle. And we've done that. So let me walk you through by some very simple analysis. So if there were no topological defects at the end, my energy at the end for my model would be simply given by this formula, which is kind of obvious if you think about it. So this is just a number of couplings that I have times the energy of the individual qubit. So if I create one defect, my energy will increase by this number, and that's something that should also be obvious because, you know, I had a spin pointing out, and right now I have one spin pointing down. So my energy increases by exactly 2 times the number of individual energy. So I can imagine if I have n defects, and if I can measure the energy, I can actually write down a very simple formula for the number of topological defects and the end in D-Wave. And what is very cool about it is that this is something, this energy, E of annealing time, this is something that I can read indirectly from D-Wave, even from the API that Danny presented. So, yeah, go ahead.
By defect, do you mean that, like, for instance, instead up,
Yeah, that's right. I should have mentioned that probably. So at the end, I will have strings of spins, and every time when the spin changes direction, I count that as a defect, right? So that's right. Thank you, Danny. So that's basically what theory tells you, and this is how the real experiment really looks. So those red dots are the number of topological defects directly measured in D-wave. I mean, we measured the energy and then we calculated the number of topological defects using the formula I just showed you. And this green line is theoretical predictions. And as you can almost immediately see, something is wrong here. And to be honest, this is something that was to be expected because, well, Kibble-Jurek mechanism and many theory that we currently have are a theory that concern with closed quantum systems. And unfortunately, D-Wave is a real chip, which means I cannot neglect anymore processes like heat exchange or decoherence. So I have to somehow take them into account. But the problem is we don't know how to do that. This is a really exciting problem because, well, something's happening and we don't have clear answer what it is. And let me only say that there are some aspects of this plot that we do understand. I don't want to talk about them further. I just wanted to show you how what kind of problems you can address with D-Wave, what kind of questions you can pose. But there are also many problems that we honestly don't know how to address. And let me be clear about something. This is really hard to simulate classically, and the primary reason for that is this is quantum many-body time-dependent stiff system. So good luck, basically, right? But as you can see, there are many features that are really nice. Like, for example, there is clearly some function. So the scaling survives decoherence. So even though we cannot predict, so the number of topological defects is roughly of the same order, which is a good thing. But on the other hand, the match is not perfect, which also tells you something. Though actually, if you compare them, the slope, theoretical predictions says that we should see 0.5. We are getting 0.41. So all the error bars are actually negligible here, and the number of the absolute value of topological defects also is not perfect. Okay. So, but I think I'm going to finish here. Let me only say that this is something that we've been working at Los Alamos, and if you have any idea how to solve it, well, give me a call. And so I think I will devote the rest of my talk to questions. Thank you very much.
Do you worry about this A coefficient or the slope? Because it's quite good, yeah? 0.41 and 0.5. This is phenomenology, but theory at the end, yes? It gives you.
So actually, it's not phenomenological theory. We for the Ising model, we have exact solution obtained by Jacek Jarmaga from Jagiellonian University. So it's not phenomenological theory. And I think both of them are important, but there are many different problems that I haven't mentioned. Is that in this regime we should be seeing some curvature of this plot, and we are not seeing that. So that also tells you something, right? So at this point we should be looking very closely to both of them. Come on, guys.
Just a silly question. How many runs of each point you've done?
500 for each.
For each point?
Yes.
Okay, so it's all on the average of the run.
That's right. That's right. But like I said, error bars are basically negligible. Mm-hmm. Well, this is exactly the question that Piotrek asked. So we average them over different runs. So, but let me only say something. It's not a D-wave problem, I think. So we don't really have a comprehensive theory to compare with. That's the issue here. D-wave is giving us some data, and we have some rough theory which is based on closed quantum systems. So, and we've been trying to figure that out.
From each run, you choose just one configuration, one result configuration.
You mean different? So what do you mean by different configurations?
Because D-Wave, as I learned recently, gives you a set, let's say, 100 solutions.
Well, it's quantum.
The value of the function.
Well, you do statistics over this data, so you basically you average them. So so I get like energy 0.5 with probability 75%, let's say, and then something else. So you do usual quantum mechanical averaging. So that's it.
What is the variance for this? You have average.
Well, very small, negligible in this plot.
So the formula that you showed a few slides earlier gave the number of defects being both a function of, it depended on J.
Yeah.
And in the graph you showed us just then, the horizontal axis was speed. Is J big? Because if you vary J, you're going to also get a different.
Yeah, that's right. So to present you with this formula, I just assumed that all couplings were equal, but in principle you can change them, and of course the speed will depend on that as well. But basically we've been getting the best possible results, setting the biggest possible value of J, and we do believe we understand why that is the case.
Are there any prospects for extended dual zerg so it incorporates decoherence and
Yeah, so this is the problem that I've been working on currently, and it's difficult. I cannot really say at this point.
Okay, so let's thank the speaker.
Thanks, guys.